Okay, we can start. Mara Salvato from MPE Germany, and we don't have a particularly strict time limit, apart from like the villa at 4:30. So machine learning applied to identification, characterization of X-ray sources and open problems.
Yes, thank you for being here. I was not counting on anyone being present except Jeff because my office is forced to come. And so I'm going to show you how we are using machine learning in my field. Saying that a fish out of water will feel more comfortable than myself now is give you an idea how I feel. I am Mara Salvato, as I say, and I am spokesperson of one mission that is called Irosita. I do not know how many of you knows about it. It is an X-ray telescope, a German X-ray telescope that is flying currently on a Russian satellite. And this can already tell you the kind of problem that we have. And we are mapping the entire sky in X-ray. And this is the first image that we have taken. It takes 6 months to take this image. There is nothing so deep and so complete currently and better than this image. What you see are the extended features, the colored one. So this is an RGB image, probably you're aware of. You combine 3 different bands, and the colors tell you something about the spectral energy distribution of the objects. There is a pointer. Yes, objects like this are extended, and they are the residuals of explosion of stars. They are called supernova remnants. I will show you probably something later. We are learning about the intergalactic medium, interstellar medium, because this is the medium within our galaxy. The red is indicating sources that are bright in the soft X-ray band. When you have dust, gas, material obscuring the soft part of the spectrum, then you see the hard source, just to give you an idea. The dots, the white dots, just because it's fascinating, this structure here that you see is the residual of the jet that was coming from our black hole. As you know, every galaxy has a black hole. Sometimes it is active, sometimes it's not. And when it is active, it has a jet, and then it can turn off, and you still have in the medium the trace of what was happening. So this was one of the first discovery of the mission, that we were finding these features indicating past activity. Just to put everything in a context. The white dots that you in an optical image will be cosmic rays, unknown feature that you want to get rid of. This is noise. In reality, are our treasures, because these are either that are emitting in X-ray, or these are galaxies that have the black hole that is active, and these are objects that we call AGN, active galactic nuclei, and we do science with those. And just to, yeah, here I was, I have the same image, but with the name associated to objects that we know already. They have, as I said, supernova remnant, so the residual of this explosion of the stars, or when they are fuzzy in this way, these are clusters of galaxies. This means the hot gas, so the X-ray trace the hot gas that is within thousands of galaxies. So it's not only one dot is one galaxy. Here, there you have many thousand objects, and this by itself is fascinating. What I'm going to present today is the work that I am doing on the white dots, because I am in charge with the task of identify them, find which are at other wavelengths, decide whether they are galactic, so from our galaxy, or extragalactic, and also measure the distance, because without the distance, we cannot do anything. And essentially, my task is done in 3 phases using machine learning now. So far, it has been done with brain learning. So I will show you how I applied. This morning, you were saying I am human, so I will show you what I've done in all these years of my work. And until Irosita, the objects were too few to apply machine learning in a reasonable way. Now what we are doing is using what we have learned with our brain, teaching a machine learning, and then taking from there. So I hope to be able to show you what I've done and the problems that are open, and probably your input will help in solving some of the issues. One thing that I wanted to keep in mind, these are the wrong orders, so let me go on this one. Focus, ignore this part first and look at here. Every galaxy has an history. It has a different type of stars, a different type of gas, it evolved in a different way. And the history of the galaxy is, included in the spectrum. This is the optical spectrum, a galaxy that extinguished all the gas, so there is no star formation going on. It is a passive stars. There are many other types. If I manage to making them, sorry, I'm in the wrong order. So these objects will have a star formation because these lines are appearing. Different type of objects. This object has definitely a black hole that is active, and so on. Taking the spectra and identifying the emission lines allow us to get a quantity that is called redshift, which is directly connected to the distance of the object from us. And one way that we are using this information with the redshift is, for example, measuring the number of objects split in luminosity or shape and distance. See how the number, make models of galaxy evolution. So without redshift, we cannot do anything. It is our final goal. In order to get the redshift, you need to have a spectrum, and the spectrum takes forever to be taken because these X-ray objects are rare, and you don't take them, either you take them one by one, it will take forever. And even if you have a multi-object spectrograph with many slits available, still it takes forever to go all over the sky. So we have a trick that instead of having redshift from the spectrum, which is the ultimate dream, if you like, what we do is we take photometry. So in front of telescopes that can cover large portion of the sky, we put filters of different that are able to block the light at other wavelengths. And for each object that we see in the image, we measure the flux. And putting together the flux from different wavelengths, we then reconstruct the profile of the objects, and we match it with the profiles of galaxies that we have learned existing from the spectroscopic sample, okay? And not only we fit the data in order to get properties as I've said on the history of the galaxy, we also try to get the information on the distance. And this is going to be causing some problem. Not only we need to have, so at the moment we have a photometry on the entire sky. Here you have the universe as we see it from Earth, if you like. These are all surveys at different wavelengths, and essentially every point of the sky, wherever you're looking, it is covered now by at least 10 photometric points in optical, near infrared, mid-infrared, optical, and UV, okay? And the problem that we have is to associate to the X-ray source the right optical source. And once that you have it, you have to collect, to make a patchwork of all the photometry coming from the other survey, because only in this way you can create the spectral energy distribution. But as you see from this plot, which is kind of, you have here the length of the line indicate the width of the filter that's been used. And we go from UV, X-ray to radio. And the number, the height in this plot tells you how deep are the data. Data that are here are extremely shallow, so they will see only the objects that are very bright. Areas, objects that are observed with these filters, with this survey, are extremely faint and go farther away in time, okay? Good. So this is the background that we have. Now started to discuss the problems. In the past, when we wanted to get the X-ray, sorry, let me work because I realized that maybe having another plot in front would have been easier. Let me see if this one tells something more. No, I do not have it. Okay, then I will draw it. We go on board. Things to remember. There is a relation between the flux in X-ray and how precise is the coordinate that you have. We call it positional accuracy. And for X-ray telescopes that are currently in sky, Chandra, XMM, maybe you have heard the names, they are precise, and it means that they manage to have a precision in a positional accuracy that is very high, also at faint flux. Here is a flux going on, okay? It means that here, let's say 1 arcsecond. So it is very easy to get from an X-ray position the corresponding object in optical. For Rosita, because it is focused in getting the scan of the sky as fast as possible, we pay off in accuracy, and our accuracy is actually 30 per second. This means that we have like thousands of objects corresponding to one X-ray source. So if an X-ray, and you will see later some figure, there are plenty of objects, we have to be able to identify who the guy is, okay? In the past, what was done was the following. People will take an optical image, they will count all the sources that are within the, so the red circle indicates the position of an X-ray source. They will count all the objects that are within that circle, and they will make the histogram of the flux distribution. Instead of flux is the logarithm of the flux, is a magnitude, okay? But essentially is a flux. And they will take circles of the same size in a random position of the sky, recount the objects, remake the histogram, and this will be the distribution of the source in the field. From the ratio of the two, they will get the expected distribution of luminosity of an object that is associated to an X-ray flux, okay? And this will be how it was done until about 3-4 years ago. Say it again? I am, because what I need to do is from the X-ray source, I need to get, for X-ray source X, I want to have for each galaxy, for each object in the field, what is the probability to be associated based on the magnitude of the guy. So I will associate a probability, and then I will go to the telescope and get a spectra and go on with my science. So at the end, I really want to have X counterpart, and so on, okay? And now the problem starts. In principle, this could be the solution. Here, the plot that I want to show was in the wrong order. So this was telling Chandra as a very precise position. So you will immediately identify the counterparts. If you have stuff like that, everything could be the X-ray emitter. Now the fun part. Depending on which image you look for finding your counterpart, you are getting different results. So this is an example. You have an X-ray source within the green circle. Zeta indicate an image in the filter band Z, which is about 1 micron, a little bit less maybe. K band is 1.8 micron, and B band is in the optical, so 3,000, 4,000 angstrom, okay? And the white dots are objects. And my question to you is, can you tell me of objects in which band I have the right guy and which is the right one? Yeah, it's not obvious. Everybody will go for this one because there is a right an object closer to the center, and statistically we'll say this is the closer to your X-ray position, this is our guy. Instead, the correct guy is this one. And we know it because in this specific case, we also had Chandra, and so we could really pinpoint our guy. But the message here is that if you apply the method as it was done before with the maximum likelihood, you will repeat all your exercise one band at a time, try to understand for every band the best result, try to guess with some expertise, with your own experience, which is the right counterpart. And this is, of course, impossible when you have an all-sky survey. There is also something more interesting, and it is the fact that, so there is one thing to say, you can combine in Bayesian statistic all your catalog at the same time and actually account for the probability that your object is the right one, also accounting for the fact that in some band, your object is not seen. Okay, so the code that I made my student doing, we create a Bayesian code. It is called N-way, just because you have N catalogs. And we combine very different catalogs and compute the probability for each guy to be the right counterpart. So we will combine the information from this guy, take into account that is not seen here, that this guy is only visible here, and so on. And the probability is based on separation between the X-ray and the optical, positional error in X-ray and optical, and number density of objects in X-ray and in optical. However, what is nice with the Bayesian approach, as you know better than me, is that you can multiply different probabilities. So what we are doing now is not only taking into account the spatial distribution of the objects, we can also multiply for the probability that an object has a certain property. And the properties can be defined taking in mind that if the object is visible in zeta band, not in K, and in B band, what is happening is the following. So if I put these slides in order, I have B, Z, K. The object is visible in Z, not in K, and very bright in B. So this guy, if I put here flux, is going to do something like that. The B guy number one, this guy here is only here, probably is a star. And this guy here is very bright only in K, so it's going to be something like that. So this is telling me something from my object. So if I take the 20 years of Chandra observations with objects that are super known, I look at the distribution of their profiles, I can use this as a prior to distinguish between objects that are emitting or not emitting. And this what is the first application that we have of machine learning. We took 24,000 objects that we know were X-ray emitter. They are stars, normal galaxy, AGN, passive galaxy in a cluster, and so on. Learn their profile and then applied on as multiplicative in this code. This was the first application. We have learned, and this is the first example of brain learning. We took these objects and we realized in this survey, this is a ROSAT survey, which is a precursor of Rosita. We noticed that all the sources that were X-ray detected in mid-infrared band, so this will be 4.5 micron, and this will be 3.6 minus 4.5 micron. The gray objects are actual X-ray sources, and the yellow sources are everything else around. So our objects have a clear location in sky. We transform this as a density plane, and then we use it for finding our counterparts. We were super happy, but if you take fainter X-ray sources, you start to get your objects that goes on the top of the field, so the prior doesn't work anymore. Or if you go closer to the galactic plane, where all the Milky Way is visible, you are dominated by stars, and the stars can be everywhere. So our prior that was so successful is going to fail completely. Means that we cannot use only W1 and W2. We needed to increase the number of parameters. And this is what we have now. So currently we are getting, we are using not only W1 and W2, we are also using the flux in the GRZ band. We are also using the information coming from Gaia. I don't know if you know Gaia, is the satellite that is mapping all the stars in our galaxy. We are taking into account whether or not the object is moving. If it is moving, is a star. And we are using the difference of these fluxes because the colors will tell us the slope and so tell us how the profile of the object is. And using random forest and all this, we are getting an accuracy and a completeness and purity of 95%. So we are really successful and it is working. So very happy about that. We have now solved the first problem, identify the counterpart. And now the question is, my goal is to split galactic and extragalactic sources because I needed to give the sources to the right people because they had to do the science. And this is another brain learning. What we take a counterpart. If we have the redshift or if we have the spectra, we know whether or not it is a galaxy or an extra or a galactic of extragalactic source. Then we take the sources for which we know the redshift or the characterization and found a plane where we were able to separate them. So here you see a combination of filters, flux in various filters, where I plot in dark blue and dark red objects that we know are galaxies, so extragalactic objects, and objects that we know are stars, so objects in our galaxy. And realized that there is a really this nice, almost natural division between galactic and extragalactic. And so it was easy then to say, okay, whatever is on this side is extragalactic, light blue, and whatever is here is probably stellar. Here is definitely all stellar. Here we have a mixture. And we were successful in this separation for about 98%. So we were very happy. We solved the problem. We are able to distinguish the objects and we can go on. Unfortunately, it's not the case. This work was done using a limited amount of data. So this is the entire sky. And all the data that you see there are coming from an area that is like that. So instead of 40,000 square degrees, 140 only, and completely away from the Milky Way region where you have the stars. And if you then try to apply this method to the whole sky that I was showing before, it doesn't work. We have issues, and we wanted to find an improvement. So here you see the result of the empirical method, the one that I was showing before. And now this is the approach with two different machine learning, logistic regression and Fisher linear discriminant. And actually you see that we are doing very well. And of course, we had to add more parameters as I was showing before for the separation. So this was the result. So I'm missing one slide because the students sent me the result like 1 hour ago. So this is the quality of the machine learning using only these 4 parameters. When you apply them to the entire sky, it doesn't work. And I show you in this slide why. So sorry, they are inverted the slides. So IFEDS was this part of the sky, and this is the same plot for the entire sky. And you see the feature is exactly the same, right? You see, this is the line, so these are the stars. But in reality, for the entire sky, you have much more that was not represented in the 140. And so we had to, as I said, retrain, use more parameters, and now, another addition, sorry. We know what we have here using Gaia, some of the objects are already classified as star in black and as galaxy in Gaia. So we are using this information for retraining. And now we are back to at the level before. Now we are at 98.8%. So also this is done. So we have no problem. Now the difficult part is happening. We know the objects. We know if it is a galaxy or it is a star. If it is a galaxy, I need the redshift. And there are various issues. One of the problems is degeneracy in the solutions. Here I'm showing you the plots that I was showing you at the beginning when I was showing you the spectrum of different types of galaxies. And here you have them all together. This is an object that doesn't form stars. This has some star formation. These are objects that are strongest star formation, and these are two objects that have a black hole that is active in a different way. If you take these very strong star-forming objects, and if it is a redshift 0, it has the profile in this way, and this is the wavelengths. If the object is at redshift 1, it's going to move in that way. So when we take the photometry in two different filters, for example, I and Z, I can follow how color, we call color the difference in magnitude, evolve with redshift. And what you see is that there are objects that have so many features that you can identify the solution almost univocally just with two photometric points. There are objects like the AGN, the black hole active guy, that's practically flat all over the range. And this because the black hole is actually a power law. And in the power law, there is no way that you are able to fit and identify the distance. So what we do is combining many of these bands. So not only I minus Z, but R minus I, U minus V, and so on. This is a sketch showing essentially the way in which we computed the redshift via photometry redshift, and the people that use SED fitting, which is the empirical method that I normally use, simply take the photometry and fit with different templates of galaxies until they are at a distance, the minimum photometric points. The machine learning people pretend that they know nothing and try to guess the distance. But essentially, they are using the same principle. Simply, they refuse to admit that there is physics in this part. It is true, it's not magic. They are using something that is there. They simply pretend that they do not know it. And I realized that I killed one of the slides, which is the one that makes the difference. Give me a second. In a remake, so I have to tell you the story. I was making the presentation. I discussed it with Jeff. I realized that I needed to have more information. I remade it and I lost one of the information. Give me a second. Where are you? Okay, we go online. But it should be YouTube. Sorry. Because with the video, you understand much better. Here, the guy. Yes, animation. So let's stop it 1 second. So what you see here is an animation that tries to explain the spectral energy distribution of an AGN, a galaxy with a black hole that is active. You have optical bands, mid-different, soft X-ray, and hard X-ray. The power law here is the part that is coming from the black hole. Emission lines are either from the black hole or for star formation. The red part is the dust that surround the black hole And depending on the intensity of the black hole is heating up the dust. So this will have a different intensity. And the gray guy here is just one of the many galaxies that I had before in my profile. And now what is happening is that depending on how much dust there is in front of the black hole, the entire sum of the various components, which is the black line, is going to change. So you will see, you see here how the result is changing. Here, the fraction tells how intense the AGN is, and again, how much dust level is there. So my goal now is, with the limited amount of photometric points, I need to guess the redshift. And sorry, I go back here. So now we have two problems. We have that. Why did I kill it? Say it again. I was not. Can you speak with it? Is somebody able to speak with the machinery? I'm not. I'm really sorry. No, I killed the sharing, sorry. Yeah, I'm sorry. Okay, so let's go play again. So we have now two problems. We have the part where we have that every AGN is the sum of a galaxy and a contribution from the active black hole, and the relative ratio of the two is unknown and is going to be visible in different wavelengths range. And then we have that is not only one galaxy, but can be many galaxies, different types that are hosting the AGN, and they all have their own degeneracy. And I'm trying to make sense of it. Again, this is something that I started like 13 years ago. I learned by experience is that if the objects in the optical image is small, is large, say, it can only be nearby. And this means that they can add the prior and say, computer, don't go at a distance larger than a certain amount, because physically it doesn't make sense. This object cannot be farther away. And if it is a dot, instead, it could also go very far away. And one part that I didn't tell you is that AGN are actually varying in time. So all the photometry that is collected over the years mapped in the sky are not simultaneously done. So if the object is varying, my photometry is not able to detect that. So I have to account also for variability. So depending on whether the object is a point-like, this symbol means point-like, a QSO-like, and variable, then for sure it has to be dominated by the black hole. So I am limiting the number of templates that I'm using. If it is large, extended, it can only be nearby, and it has to be dominated by the galaxy, because if it was dominated by the black hole, I will not be able to see the galaxy. And so I use all these informations for getting this. And this is the redshift as it is known, and the redshift that I compute. And as you see, I'm doing decently well. So the accuracy is this, the number of outliers is this, but it is, I have two problems. I have creating too many objects in the higher universe, and these screw up all my galaxy models, galaxy evolution, because they do not make any sense. And I am degrading my results a lot if I remove photometric points. So I had told you that the entire sky is covered by many photometric points. Unfortunately, not everywhere I have sufficient points. So my quality depends on the number of photometric points that I have. And with this accuracy, I cannot do anything. Science cannot be done with this quality of the data. So now the question is, is there a way for me to improve my results with the limited number of information? Or I reached the end of the exercise and say, as long as people are not going to give me other photometric points, there is nothing I can do. And in order to understand better, what we are trying to do now is working with machine learning, try to understand the limitations. Machine learning seems to work. It creates, this is machine learning with a work that we did with Massimo Brescia, one of the organizers of this meeting. We get less, this is redshift spectroscopic, and this is difference between the redshift computed and the spectroscopy divided 1 plus zeta spec. Here is the high redshift universe. I have less objects. This will be my work with SCD fitting, but the distribution is much broader. So I will tempted to say that I like maybe this one better, but I need to make something that remove these objects. But again, this was done in the best condition where every photometric point was available. And if I just remove them, we don't manage to do the work. So one thing that we are trying to look at with this machine learning is not get for, say, every source, let's say source number 1. Here we have the U band, B band, G band, R band, W band, whatever. And here I have the flux so that I construct the SED. What I'm trying to use is the information that come from the images. So in every image in these bands, I have that the object is looking in a different way. So in the U band, I will have that I am dominated by star forming. So if the object is formed by a black hole, a bulge dominated by passive old population stars and new stars in a spiral, in the U, I will see mostly the arms and the black hole, because the black hole has the power law in the center. If I'm using the zeta band, I will see mostly this component. And instead of using directly the images, what we have is a measure of the flux in various apertures. So I have that instead of a number, I have a matrix, an array, sorry, of 7 points, where in each of them, I have the flux within an area, within the next, and so on. And so we are, this is the representation. You have the arcsecond, and these are, this is the profile of the same galaxy in different bands. And using this information with machine learning, we are actually doing pretty good in one type of object using only 4 bands. So not 11, 12 as before, we are doing well. But we are doing well only on the sources that are dominated by the galaxies. The objects that are dominated by the AGN so far were not coming out very well. So there was a limit redshift 1. And this was mostly because the samples were not big enough. Now we are accumulating data, and the latest results are here, where we have a training sample, validation sample, and validation and blind test. Here you see the distribution, and it looks good because essentially you do not have the high redshift part that we have here. So I am not creating fake high redshift objects. It looks good, but if I look at the numbers, still is not optimal. So we are just at the beginning of the story. Yes. This is a fully convolutional neural network. Huh? Yeah, neural, yes. We put in all these metrics, essentially. One thing that is interesting is that the method, they were assuring me that the method will have learned also to try to make the ratio of the fluxes. It will have tried it. And this will have made sense because when I look at the SCD fitting with the wavelengths, the ratio of the flux is providing the slopes, right? And instead, the best result is obtained making the ratio of the flux. And so instead of counting on the machinery doing it, you tell you, no, you do it. Actually, is working better. But the problem again is that we do not know yet whether we are on the right way or we reach our limit. And what Jeff was saying in our conversation was saying that maybe, and now we will discover that I didn't understand anything, is that instead of spending much time in trying and not know where to go, try to make a model and see using the model whether you reached your limitations or there is room for improvement. And this is all what I wanted to show you today. Thank you. Opinions, questions?
Thank you.
So the images are not in my possession. The images are prior to possession of another team. And what they release to the public is for the million sources that they have, the array of values in each of the bands that they have. So I'm working with this data. The legacy survey for DESI, DR9, DR10. So the DR10 is going to be available in a couple of months. We are working on it, but at the moment, we are using only what is public available, no images. How many points? So these are at the moment is GRZ, W1, W2, W3, W4. And then we combine them with 3 bands in mid-infrared, and then we add 2 UV. But the UV and the near-infrared are only available for the bright objects. So a lot of the issues that we have now with the machine learning here is that we do not have photometry for all the points because some of the data are too shallow. And the missing data is not because the object is not emitting there, it's just that the data are not deep enough to measure, so they're like upper limits. So we needed to learn how to ingest the upper limit because it is a quantity that it has a meaning, an information. The machine learning problem is that it provides at the moment, unless you're working with maximum F for the redshift. And instead we need the probability distribution function. So I'm very interested to the talk of tomorrow. I don't know who is the speaker. You are. No, I was counting. No, that is unfair. I was really looking what. That is very bad. Okay, I was really counting on your talk for having a way to estimate the probabilities. Okay, okay. Probably this comes from my ignorance. So this is my students, and I ask, why don't you try in that way? Because and then I learned that with images. So for me, this is an image, right? And so for me, that is an image. It's a very tiny image, yes. So you have a really, you can distinguish the shape, you look at the concentration. So if there is always, maybe I can show you this one, I didn't show it, so I can, If I look at this object that I was drawing, you had the black hole, the bulge, and the spiral. If you look at the profile, it's going to be like that. And from the intensity of this component, so this is an image, essentially. The radio profile, yeah. Scaling as in a zoom in and out. So the object, this object will be of this size at low redshift, and going at higher redshift, it will be zooming out. Because there are, I mean, more or less, until a certain point, the galaxies are kind of the same, at the same type, the same profile, at different distance.
It's just if you can help, and then it was a spectral piece or radial or but actually in this case it depends to be either smart or useless. Another one, because you got data, you mentioned, and then one I mentioned is this is the wavelength, right? The bands, and the other I mentioned is the spatial. I think it connects what you were saying. It makes sense to actually do the convolution on spectral direction. So the convolution layer basically the main ratios of the filters, which is exactly the makes ratios of the filters, and then does this for all the radio slices, and then you have the dimension to make it convolution. That Jen was saying, if you put the convolution on the spatial, then you are dealing with this rotation nodes. But I don't think there's too much information to extract locally at 7 points.
Mm-hmm.
7 points. But yeah, I mean, it makes some kind of sense, and probably doesn't really matter in the end. Find whatever. Maybe you can check if you can eat very, very, very easily your evolution with a fully connected. It's 20 by 7, 24 points, directly fully linearly connected. If you just do a linear with the full network, and you obviously do better in the beginning or like 2 days on fire, you probably feeling the other information.
Mm-hmm.
It's like you're doing convolution, they're really small. Yeah. So what is the filter usually in convolutional network is like bigger than you got your data. Yeah.
So what would you use since you are confused by the method?
It's not a lot. It's not a big piece of data. It's fixed in your machine learning. Like, yeah. So it's not a big change.
Mm-hmm.
Good question. More or less, I get what is the input, but I cannot relate the data. I understood about the input with the problem. Is this a classification that we want to do?
No, there is a distance of the object. So we take 5,000 objects for which we have this data and the distance, and we try to guess the distance of the other objects using all the photometry. These will be the photometry in the G band, R band, I band, Z band, so the one that I was showing before. But instead of having one number per filter, that will just provide you the spectral energy distribution in this wavelengths regime. For each of the bands, I'm getting information on concentration distribution using the flux included within a certain distance from the center of the objects. Okay, so the shape of the light distribution in every band for each object. So practically is a spectral energy distribution that depends on the distance from the center. Yes, so we are using also the errors as, yeah. So it's not only the flux, it's also the error. The only thing that we did not manage at the moment is to include the known signal. So we are limiting the sample to the objects for which we have the photometry in all the bands. I should have sent my students here because I should ask. We went through the catalog and I said I wanted to include this and this and this and this and these parameters. So I am explaining, we have no the expertise, but we have a university close to us and they have a section dedicated to people that work with machine learning. And we have an agreement and the professors allow the student to make internship with us. So they are training the expertise and they apply their method to our data. We are definitely not experts. Yeah. He does, but we are not getting an error associated to the output. And that is the other problem.
But the way of building a natural that I do not know. Nice. I trust the thing, but in principle, for sure, something that gives you an output. And you don't have to test for probability. There is a nice course online. I learned that way. I do, but I still don't know whether I should believe them or not. It's a spiral. No, I think it should get instant goals, right? Most places, yeah, but it's also that in principle you can not only study your weights in a probabilistic way, but maybe also the called systemic uncertainty. So I'll look into a model in general, right? Because I see that a weight or distribution of weights to me doesn't change anything in terms of interpretation, right? So it's like all of that line the points and then the line starts addressing graphics. Maybe you work space time whatever and you're getting steers for A and B, and now we're doing the same thing with all the weights in the thing. And it's like this is the more principal way of doing weights in networks in which you know by incidents. So it's too annoying. The other thing is the ensembles, which is way more complex. You like the way it's done, but you get like variation of steers on the weights doing derivatives and you do get then you sample this, then you sample weights.
Yeah.
After the input data, sample from the steer then you sample new weights. You're not going to get much predictability, but you know what I'm saying, right? It's just that you have to have a bar associated with your prediction, but then what you need is not really right. You just want a fancy version of error propagation. Exactly. You gotta take those errors and push them through this whole thing and see what they from. Yeah. So. Okay.
Yep.
There are probably a bunch of people doing this. I mean, what we see is the problem.
Yeah.
and there will be
Mm. Yeah, so we are, this plot is actually coming from other people. This is not us. The problem that we have is that all these people are interested in objects that are not AGN. They are working only on galaxies, and galaxies have specific features. If you remember the plot that I was showing before, this one, this is a type of galaxy, and you can clearly find solutions for your redshift. So again, this is one color, and it is almost, there are very few alternative solutions for the redshift to have a good fit. And if you have many colors, the solution become really unique. And here you have the multi-peak for the non-active galaxy, so elliptical. In the blue, you have a strongly star forming. At the moment in which you have the active black hole, it becomes a straight line. And this is not a problem that people working with Euclid or any other survey have. And we have this power law, you know, I can have as many points as I want. The fit is not going to change as a function of redshift. And so unless I find a different features that is not flux, but maybe is a shape of the entire galaxy, I cannot break the degeneracy there. And because the AGN are a few percent of the normal galaxies, the majority of the people do not care to have this problem. So they come to me, I tell them, this is an AGN, this is an AGN, this is an AGN. So they remove this object from their sample and their photo Z is perfect. I'm interested in what they are trashing. Correct. Yes, so this is so this is something that people use also working on galaxies. They use as a prior the distribution of the type of object as a function of redshift, because you have that local universe, you have more I don't know, star forming or more elliptic, and you can use it for AGN. You have the problem that the luminosity, in order to do the luminosity function, which is the one that is used number of object distribution as a function of redshift, it is unknown because we are missing the redshift in the first place. So all my work is done for creating at the end a better model of how AGNs are evolving as a function of time. And so we are still missing that information. All the information that we have comes from X-ray surveys done in pencil beam areas, they observed very deeply, so a small area of the sky. And in this small area of the sky, the objects that you find are AGNs that are very weak and they are dominated by the galaxy. What we are missing always are the bright AGN that were missing from the surveys because they are rare, and you need to have Rosita to detect them. So this is a completely new parameter space that was not existing before. We knew that it was missing, we could not make the model. And now that we have it, the idea is getting redshift as accurate as possible, make a model, and then use this model for the next generation of X-ray surveys. Yeah. Yeah. They do not, they are not good models. The semi-analytical put the seed of the black hole in their work, but they are not making luminosity of black hole plus the host. The best result yet is still empirical. So you take objects that you know that are for sure hosting an AGN, you take the spectra, and actually you really attach spectra at different wavelengths, not only in optical, but in infrared, mid-infrared, UV, so that you learn how they are done and you use those for learning. We are still really at the beginning of the science.
Whatever you showed that movie.
Yeah.
So whatever was creating that movie.
Yeah, but that movie was done for the objects that are not dominated by the black hole. There was always some obscuration level. The objects that Rosita is finding are actually with a strong component from the AGN part, and this is the new population that is missing from the luminosity function. So the distribution of objects as a function of redshift, those are still missing. The model that I was showing in the movie gives an idea in how the contribution from the black hole and the host change, but it was done under the assumption that there is always some dust that is hiding part of the luminosity, while I'm working also on objects that are non-obscured. So there is an additional ingredient to that movie that is not discussed in that movie. Yeah, it will be just a pure power law. So there is something that we are doing. So the idea of Jeff was to generate all these possible models and try to learn from them and use them for making our guess. One part of our team is working on the objects for which we know the redshifts, and we try to decompose the flux that is coming from the AGN, taking it away, focus on the light of the galaxy, because looking only at the light of the galaxy, you learn about the age of the galaxy, how much star formation, the history of the star formation, and so on. So this is the part that we are interested in, removing the AGN component. And in order to test our models, we have created empirically, we took real AGN dominated by the black hole only, real galaxies, combine them together with different proportions, and we are using them to see whether we can recover the right fraction of AGN. We never thought to use these objects as model for our work. So this is the end of our conversation of 2 days ago. So indeed, I will go home and try to see whether these models that we are using for learning how to decompose the black hole from the host can help in solving the problem. But it's really work in progress. Yeah. Yeah, it does not have the information on how many of those are present with that ratio at that redshift, because this is really an unknown, while a semi-analytical model also comes with the information on number aspect of objects per type at certain redshift. Yeah. 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 So we have, you have that an object is defined by the host, and the host is defined by the amount of gas, the amount of dust, and the type of objects. Then you have the AGN, the black hole part, which depends on the mass of the black hole, the spin, which then affect the intensity of the initial lines that come from the black hole. So at the end, we have like maybe 7, 8 parameters that we have to maybe 10 if you want to keep it as general as possible. So it's equal to the number of photometric points, essentially, the number of parameters that we have. Good. So we have at the moment, we have a sample that is decent. I would say on the order of maybe 20,000. But you know, they look a lot, but they are not, because if you split them in redshift and type of galaxies and AGN intensity, at the end you have more typology than, so the subsamples are very small still. Yeah. But it was something. Yeah. 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 But there are two types of supernova. While for me, AGN and galaxy contribution can be really changing dramatically. And if you have the black hole that has dust in front and it is oriented different from the galaxy, you create yet another object. So the... Yes. Yeah. Yeah.
There should be a best solution which we just use that.
Yeah. 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 And then you, yeah. So yes. So just saying, we finished the identification of the sources last summer. So means 2 months ago. So we is really at the beginning of the challenge in improving the redshift. I've shown what we have done in testing with Massimo Brescia and what we are doing with the group. Also coming here, I have ideas in how to go on with the work, but hopefully we will manage to get some results.
Okay, so I think
it was more than half an hour.
That
was.
Thank you very much.
Thank you.